I'm going to introduce the second speaker of this morning, Professor Hanoch SENDEROWITZ. Professor Hanoch completed his PhD student in organic chemistry at Tel Aviv University, and then he did a postdoctoral training at Columbia University. Upon his return to Israel, he joined the pharmaceutical industry, first at Vector, and then at Epic Pharmaceuticals. He then moved to the Department of Chemistry at Ilan University, where he's heading the Laboratory of Molecular Modeling, Computer-Aided Drug Design, and Chemoinformatics. A major focus of his research is the development, implementation, and usage of molecular modeling tools and machine learning algorithms in various fields, including Chemoinformatics, Materials Informatics, Informatics, and Forensic Informatics.
Thank you, and sorry, and thank you, Sasha, for inviting me again to this place. And talking after Alex is always a challenge. And actually, all the previous speakers set such high bar that I hope I can match it. So I'm going to talk about materials informatics. And as you can see from the number of publications, this is a rapidly growing field. Now, I have to open your parentheses and say that terminology is important, because if you look at the literature, a lot of people are actually doing materials informatics, they just don't say it. So I think this number of publications is just the tip of the iceberg. And again, something which is somewhat related to what Alex just said, working in this field, I found that many people working in different fields are doing the same thing, just calling it by different names. And assuming that most of us here are chemists, I should say that chemists have been doing machine learning for about 60 years, starting from the early work of Corwin Hansch. But we can close this parenthesis, and we can ask the question, what is driving the increase in material informatics? And as in many informatic-related areas, this is basically by data. So we have more and more data, and some of them are shown here. So for example, the inorganic chemical structure database contained, as of yesterday, I think, over a quarter of a million crystal structures. The NIST contains a lot of information. It contains 102,000 very accurate materials and their property. The NIST is also involved in the Material Genome Initiative. And if you want, you can read the idea behind the Material Genome Initiative here. But these are a lot of data and more accumulating. Now, most of them are experimental data. However, we have a lot of theoretical data as well. And this is one example. This is the AFlow library. It's completely open. You can download from it whatever you want. And it contains a huge number of properties calculated by high-level ab initio methods. But all of this is only the tip of the iceberg, because the size of the chemical space or the material space is in the order of 10 to the 30, 10 to the 50, pretty much pick up whichever number you like. Okay, so a lot of data which are driving the field, and this obviously creates for us the well-known problem. We are drowning in information, we are starving from knowledge, and I'm sure all of you have seen this type of graph, the knowledge information gap. And the idea is that materials informatics can hopefully bridge this gap, or at least take some step towards bridging this gap. And most important, material informatics can take advantage of sister fields like chemoinformatics, like bioinformatics. And actually, it is instructive to compare the state of material informatics with the more mature field of chemoinformatics. And in chemoinformatics, I'm now referring to kind of classical chemoinformatics, which was originally developed perhaps for drug design. So in order to make this comparison, let's see what is needed in order to do structure property prediction in material informatics and in chemoinformatics. So we need accurate experimental data. We need activities defined in the broadest possible way. Whatever you want to learn could be defined as an activity. This will be the dependent variable. We need descriptors. They can be structure derived, they can be process derived. I'll get back to it in a second. They could be measured, they could be calculated. We need a mathematical model, which will be qualitative or quantitative, supervised, unsupervised, whatever you want. And we need a model validation. Now, we all know today that models should be validated, developed on a training set, validated on an independent test set. We also know, or at least we hope or want, that models should be simple and interpretable. And when we are going to deep neural network, this is becoming a problem, although there are now methods to interpret deep neural networks. But this requirement form up perhaps a nice background to compare chemoinformatics and material informatics. So in terms of the compound, in chemoinformatics, or classical chemoinformatics, the compounds are usually well defined. Drugs, heats, fragment, lead-like compound, drug-like compounds. There are some exceptions, polymers, mixtures, which are not always well defined, but even in these cases, at least we know the component. We know the monomers, we know the components which make up the mixture. And if you're doing combinatorial chemistry, this is also true. Now, in material informatics, this is not always the case. Sometimes the structure are well defined. Sometimes you actually don't know what you are studying. The structure could be completely undefined. And this is typical of combinatorial material synthesis, which I'll mention again in a few minutes. Data. So if you look at if you think about chemoinformatics, most of the chemoinformatics is primarily concerned with pharmacokinetics and pharmacodynamics. What the drugs do to the body, what the body does to the drugs. The diversity comes mainly from the target and ligands. We have many targets, we have many ligands, and the diversity comes from here. But the endpoints are not that diverse. The data set are medium, large, very large data set. Now in material informatics, the situation is slightly different because the diversity comes from the activity and from the endpoint and from the nature of the materials. So I'm listing here just a few endpoints, but there are probably hundreds of different endpoints, okay? So this diversity of endpoints comes with a price, and the price comes in the form of the databases. So even now you see material informatic models derived from tiny databases. This is when the materials are very expensive or when the experimental work needed to derive them is very costly. So you have all the range from tiny, small, medium, large, very large data set. And again, there is a huge diversity in endpoints. Descriptors. So here is another important difference. Again, in classical chemoinformatics, we usually rely on 1D, 2D, 3D, 4D, 5D descriptors. There is some usage of quantum mechanics derived descriptor, but this usage is rather limited. We usually don't do QM calculation on drug-like molecules, although sometimes this also happens. Material informatics, yes, you can do this, but there is a heavy reliance on quantum mechanic calculation, which makes the whole process much more costly. There is some reliance on experimental condition, and there are quite a few number of machine learning models using experimental condition as a descriptor. And actually, this is great because experimental condition is something which, at least in principle, you can easily manipulate. And this is not always true for the descriptors. And there is a heavy reliance on measured descriptors, and in particular on spectra. And again, in kind of classical chemoinformatics, we usually do not look at the spectra. In material informatics, not always. A lot of time we look at the spectra, and the spectra can be whichever you want. Raman, IR, I'll show you element and analysis spectra, NMR spectra, whatever you want. Spectra are useful descriptors, either the raw data, or you can also treat them as images and process them using images method. Okay, what about algorithms? No news here. So chemoinformatics have developed many algorithms, and at least until now, I don't see any need to develop specific machine learning algorithm for material informatics. What we have for chemoinformatics is usually sufficient and works well. What about validation? So chemoinformaticians have been working on the validation for years and years and years, and we all think we know how to do it. In material informatics, this subject is less mature, partially because of the small data set. So even today, you can find a data set which were not validated on external test sets simply because there are not enough data. So in a sense, material informatics today is where chemoinformatics was like 5 or 10 years ago, but this is changing. And at least the knowledge or the understanding how to properly validate model exists. Okay, so I'm going to give examples from two completely unrelated fields. One is solar cells, which we've been working on for the last maybe 5 or 6 years, and one is forensic chemistry, which we've been working on for the last 2 years or so. So 60 seconds on solar cells. Very very briefly, you take a device, you irradiate it with light, you excite a photon, you leave behind a hole, you separate the electron and the hole from one another to an external cycle, you get electricity. Okay, and there are variants on this, but in principle, this is how it works. And there are several ways by which you can evaluate the performance of a solar cell. You can look at the voltage, you can look at the current, you can look at the quantum efficiency, field factor, a power conversion efficiency, which most people are looking at. There is no reason I'm showing this slide just to dazzle you. So this is a lot of solar cells from different manufacturers, different styles, different ways. You see the increase in the power conversion efficiency, just the definition. So the efficiency is the ratio of the electrical output to the incident light, and you see here the increase over the years. So we wanted to do statistical modeling, machine learning, whatever you want to call it, on solar cells. The goal was to identify factors responsible for photovoltaic properties, build predictive model, do experimental design, find new solar cells. The underlying assumption, of course, is this, that the properties of the solar cells which we can measure are somehow a function of the descriptors. If they are not, then there's really nothing for us to do. So we started with dye-sensitized solar cell, also known as Grätzel cell. So this is Michael Grätzel. He has one paper which was cited over 35,000 times. The paper in which he actually described this solar cell for the first time. And these cells are based on a dye. And the dye basically absorbs the light. So you illuminate the dye, you absorb the light, and you photo-excite it. The electron is transferred to a titanium oxide layer, which is shown here. The dye is regenerated by an electrolyte, and the electrolyte is reduced by the counter cathode. The electrolyte is typically iodine or something like this. And this is the energy levels. And these are well-known cells. Now, the dye is critical in these cells because it is responsible for photon harvesting, electron injection, and overall cell performance. And people for years have been using this metal-based dye, usually using ruthenium. Problem is that they're expensive. Ruthenium is an expensive metal. Synthesis is complex, and there's also a low molar extinction coefficient, which is explained here, but this is not that important. And knowing or understanding the deficiencies of these dyes, people have started to use metal-free dyes, which are inexpensive, easy to synthesize, high molar extinction coefficient. You can tune them, you can make small modifications which will change their property. There's only one problem, small problem. The PC is not that great. The power conversion efficiency is not that great. So there is a lot of effort into trying to find new dyes. And a step in this direction was taken where people started to work on this system, which is a donor, a pi bridge, acceptor, which is connected to the titanium oxide. So this architecture generated better dyes. So we wanted to see whether we can develop machine learning model to find better dye, maybe do virtual screening. So fortunately for us, a few years ago, a database of dye-sensitized solar cell was developed and published, over 4,000 entries. These are the main functional groups or main compound group in these cells. So we did some pre-processing to consider only metal-free dyes, no duplicates, and we made sure that the conditions which were tested are the same. So anything which was not measured under the same condition was simply removed. We ended up with this many dyes, and we built a model for these 4 families because these were the most populated. So here's the number of compounds in each family, and here's the number of compounds we retrieved from the zinc database in order to validate the model. I'll get to it in a second, but important to say is that we validated our models on compound having exactly the same substructure as the dyes. Otherwise, we would run the risk of cheating ourselves, and self-cheating is nice, but we don't want to do it. And then we decided that we are going to use pharmacophore modeling. We coined the term photovoltaphores just for the fun of it. And there is an issue here. So the work which I described was just recently accepted for publication. During the publication process, one of the reviewers said, look, I don't care whether it works or not, but why did you think in the first place that this should work? Because pharmacophores and these pharmacophore features were never intended for solar cell, right? They were developed in order to look at protein ligand interaction. So what are you doing with solar cell here? Now, I don't have a definite answer here except that it worked, but there is another thing here. I think that this pharmacophoric feature, maybe not directly, but they certainly correlate with the distribution of electron within a molecule. And solar cells and dyes are all about the distribution of electron or charges in a molecule. So this is the reason why I think it works. Anyway, we did a classical pharmacophore work using Ligand Scout. So this is, I think, a nice extension of the program. We did a conformational search, we did clustering, we generated model both for scaffold, okay, doesn't matter, both for each of the scaffold, and also we looked at the most active dyes, least active dyes across all scaffold and tried to generate models. We generated models for the high active or the better dyes. We also generated models, and I'm showing some of them here. Each one is superposed on one of the dyes. We also generated models for the inactive dyes. So in order to filter the false positive, this is some of the models of the inactive dyes. We validated the model using small-scale virtual screening, basically taking the active dyes from the database, augmenting them with similar compounds from the zinc with the same scaffold, did the virtual screening, calculated the raw curves, calculated some matrices, and eventually we focused on 18 models which looked to us good. I think we developed some like 100 models. We looked at the 18 models which we liked. We did the virtual screening. We took the zinc database, serving about 14 million compounds. We screened against the active dyes. We then removed compounds by screening against inactive dyes. We ranked the compound. We selected 35 compounds, and then we submitted them to high-level ab initio calculation. Why did we do this? Because we wanted to see whether we get the correct electronic properties of the compounds. So I'm showing you, I'll show you the result of the QM calculation in a second. These are the two best compounds which we obtained, this one over here and this one over here. And these two rings here indicate some changes which we made, which I'll get back to in a second. We wanted to calculate the HOMO and LUMO energies because their energies are important for the dyes. We used DFT with this functional and this basis set. And then we also calculate time-dependent DFT in order to calculate the absorption spectrum. Again, it is important. So we use this functional and this basis set. And these are the results we got. So why did we do it? Because in order for a compound to be a good dye, it should fulfill several conditions. So it should absorb in the UV and near IRV region. The HOMO should be removed from the semiconductor. The HOMO should have a certain energy. The LUMO also should have a certain energy. The HOMO should be, the energy of the HOMO should be above this line. The energy of the LUMO should be below this line. And here, so these are the two compounds we get. And here on the right, I'm showing a compound which is a very active one from the database. So we ran the same set of calculation on all of them. Actually, we ran on many more compounds, but I'm just showing some example. And all these compounds, and these compounds meet the criteria. This is their absorption spectra, which we didn't like that much because we wanted it to be shifted a little bit more to the right. So we made two changes to one of the compound, basically replacing this moiety, which was initial carboxylic group by a cyanoacrylic acid, because we saw in other cases that it is a good substituent here, and we switch and we change this moiety, which initially was succinamide, to this one. We repeated the calculation. HOMO, LUMO stay the same, and we got a small shift to the right, which is exactly what we wanted. So these are the two candidates. Now, Michael Gretzel was in Israel, so when he was in Israel, I tried to convince him to take these compounds and actually measure them, and he said, yes, sure, of course, and then he left, and I never heard back from him. So these two compounds are up for the take. I'll be very happy if someone wants to test them. Okay, Switching gear to a different type of solar cell, which are based on metal oxides. Why do we want to make cell from metal oxide? Because metal oxides are abundant, they're cheap, they could easily be handled, they are low cost, and they're stable. They're already oxidized, so they're unlikely to be further oxidized. There's only one problem, very small problem. They make out for awful solar cells. They simply are not good enough. So the idea is perhaps we can generate different metal oxides using combinatorial material sciences. Just to show you that this is not a crazy idea, this is high PCC superconductors, and this is, I don't know whether this is the best one to date, but this is one of the better one, and see which strange combination of metals and oxide it has. So going into strange combination of metal and oxide, which are largely unexplored today, may give us something interesting. How do you do it in practice? Well, we don't, but our collaborators do. So it's very easy, actually, at least for me, because I don't do it. You take a piece of glass, you coat it with a transparent layer, and you then deposit on it several layers of metal oxide. However, you don't deposit it on a regular manner, but rather with a gradient. And when you make 2 or 3 or 4 deposit, you get to a place, you get to a situation that each point on this metal glass has different ratio of different metal oxides. All you need to do now is hook to them small pieces of metals, place everything within a metal frame, and voila, you have a solar cell library of 169 compounds. This is a 13 by 13 array. Okay, so our collaborators know how to do it, they did it. And once you have this, you can analyze them, or you can characterize them by many factors, which I'm not going to go into it, but this make up of both activities, what you are trying to reproduce or to predict, and also the descriptors, which you're trying to use as the independent variables. So first thing we wanted to do is look at our solar cells space. So we had about 1,350 cells from 5 different libraries. These are the characteristics, the numbers are not that important. We use several methods, sorry, no GTM this time, but we use PCA and kernel PCA and isomap and diffusion map to look at the space. And what we found is that all methods are able to reasonably well separate the different libraries from one another. And we also looked at several measures to see how much the different methods are able to reproduce or to maintain the neighborhood behavior in the high dimensional space, in the low dimensional space. There are methods like trust and classification. The results are shown here. All the methods work approximately the same, including the oldest and the linear PCA. So just to show you 2 things which we can do with PCA. This one is trivial. This one just is outlier detection. But once you map the outliers on, and this is a library, this is a 13 by 13 solar cell library. Each square is a solar cell. When you map the outliers to the library, you see that they are always at the edges. Now, this may be true outlier, but perhaps because of problems with the devices, whenever you measure things at the edges, you may run into problems. So this is kind of a nice alert, which we alert the experimentalists. Look, you may have an issue here, or maybe not. Maybe these are really outliers. Okay, this is something else. And in this case, there are 5 libraries, each of which is made of the same composition, but they were treated at different temperatures. And when we plot the PC, you see that the libraries at different temperature are spread with horizontal lines. Now this and this is true for all the temperature except for the red library, okay, which is I think 195 degrees. Now, if you look at PC2, the temperature is 1 parameter. Okay, that makes sense. But the other parameter is the band gap. So part of the PC2 is attributed to the band gap. And the spread here at 195 may suggest that in this case, we are going a phase shift at this temperature. We're not certain about it, but this might be the case. And again, this is something very simple, just simple PCA. Okay. We then did machine learning, standard machine learning. On several of the library, we wanted to predict the current, the voltage, the internal quantum efficiency. What I'm showing you here in the graphs are results for the test set only. The numbers are shown here. The numbers in parentheses are when we apply the concept of applicability domain. So looking only on several of the cells. And you see that we get a very nice result both with KNN and also with genetic algorithm. These are the equations. They are not that complicated, and we know what governs the performance of the cell. This is basically the ratio between the two layers of metal oxide. And we can also generate virtual cells. So build a model, plug in numbers, and generate the virtual cells. The white areas over here indicate that these regions are beyond the applicability domain of our model. And what we see here is, and this is something which people knew, that it is very difficult to get a cell with high voltage and high current. So, and this is shown here. Okay, so this concludes the story of the solar cells. How much time do I have? Ah, great, so I can now speak much slower. Okay, so now I'm switching gear totally to forensic informatics, working with crimes. Now, there is quite a bit of work on this, but mostly dedicated to cyber crimes. And this is an important subject, but this is of no interest to us. What interests us is physical evidence found in crime scene. So, shoe prints, fake coin, ammunition, gunshot residue, DNA, glass fragments, and so on and so forth. All these could be found in crime scenes, and we're working with the Israeli police and with the European atomic agency or something like this, in order to try to see what we can do here. Now, I'm telling you up front, there is no new method used here. But this is, I think, cool applications of known method. So let's see what we can do with this. We focused on glass fragments. Why glass fragments? Because the Israeli police told us that every year they're encountering quite a large number of crimes where they find glass evidence in the crime scene, but they don't know what to do with them. So here is a car accident. You see all the glass fragments here, glass fragments from cups, windows, whatever you want. Here is a real case. So these two guys were coming out of the house one morning to drink coffee. And you see these guys holding a coffee mug. And important, this coffee mug is a part of a set of 2 coffee mugs. So here's another one at home. This is important. Let's see if this works. So the car approaches them, shoots this guy, and speeds off. Fortunately, he wasn't hurt. But in his panic, he threw the cup on the car, and the cup broke. So the police, so the police arrested someone, found the car, found glass fragment, and then they came not to me but to our collaborator, and they asked they asked them, okay, here's the glass fragment from the car, here's the glass fragment from the mug, from the set. Can you match these two? And the answer is yes. The way we do it, or our collaborator do it, is by using what is known as PIXI. I don't remember what it means, but this is an ion beam analysis, which basically you take a sample, you put it in the machine, you irradiate it with radiation, and as a result, you get the composition of the elements. And this is a spectrum, which you can use for machine learning. Okay, so in this particular case, here is the unknown from the car, here is the reference from the mug, they match completely, which means with a high probability, high level of probability, the car was in the site of the crime. Okay. But that's reasonably easy and no machine learning here. Here is a different problem. Suppose there is a hit and run car accident. You find a glass fragment on the side. Can you classify it to the type of car? Okay, so this is a much more challenging problem which requires machine learning. So in order to answer this question, we got in touch with the Israeli police. We went to their junkyard. We had a lab fun day with hammers. No, we didn't. But we got glass fragments from many cars. Here are the glass fragments. We ran all of them through our PIXI machinery. And we looked at the composition, and we said, well, let's see if we can use the composition as descriptor and build a classification model. And it worked. So we had a small data set at this point, about 96 measurements, and now we have many more which we are now processing. 13 car models, 10 car manufacturers, but standard data curation, train test split at random, repeated multiple times, model derivation using random forest and KNN. We try both of them. Nothing fancy, straightforward machine learning, model validation, precision, recall, and F1 score. This is what we got. So this is a confusion matrix, and these are the results. We tried several training tests split because of the way we measured the glasses, but overall, and what I'm showing you here is again just tested. We see a reasonably nice recall, precision, F1 score across the board, primarily here. And again, this is the confusion matrix. This is the Mazda. So we are very good in identifying Subaru. And we have some mixture. We have some issues with some of the other cars because their glasses are very similar to one another. But the hope is that once we get more models, we'll get better results. Now I have to say, I presented this half a year ago in Geneva. This was initiated by the European Commission of Atomic Energy, and the meeting took place in the United Nations in Geneva. And as I was coming down, there was a parking lot, and there were so many nice cars there. You know, the one which we don't have in Israel, Mercedes and Lamborghini. And really, I so much wanted to take a hammer, but obviously I didn't. Anyway, next thing we try to do is see what. So the result I presented now were measured at our own facilities. However, if we're thinking about something which is larger, we cannot measure thousands of glass fragments. And there are other facilities across Europe who can do the same measurement. So we sent all the glass fragments to other facilities using the same PIXI technique, and we generate a model based on all the results. And what we saw is that this laboratory, which I'm not going to name, gave the poorest result. These are the green. However, when we mix their results with results obtained with, better laboratory, more proficient laboratory, whatever you want to call them, the models improve. So this is kind of a global model, the top one, and you see that it is as good, almost as good as the best model, and better than the poorest model. This was the first diversity, and the last diversity is we said, fine, other people are using different methods, not just PIXI. There are EDS and whatever. So let's distribute this to many laboratories using different methods and see what we get. So what happens is interesting. In some cases, mixing different laboratories improve model performances. In some cases, mixing measurement from different laboratories degrade model performances. So I'll just give you one example. On the diagonal, this is this is the result obtained from each laboratory. EDS, which is shown here, is a method which is widely used by law enforcement agencies just because it's cheap. The models are very poor. When you mix them with PIXI, from our measurement, you get much better models. However, this PG and INNA, which are different methods, give great model. When you mix them with EDS, the model degrades. We think we know what's the reason for it. There is some orthogonality between the elements which each laboratory measures. But this is where we stand with this now. We now have a project on flammable liquids, gunshot residue, footprints. It's fun. It's really fun. So to conclude, okay, I hope that I convinced you, and probably you didn't need me to convince you that statistical modeling is important. In material science, it's provide insight, it's provide experimental design. I gave you some examples from solar cell, forensic, but there are many others. Challenges, well-curated data set. This is always the channel. Another challenge is new descriptors. A new descriptor more focused on spectra. I think we have not all, but most of the descriptor we need for chemoinformatics, classical chemoinformatics. This is not the case for materials informatics. And as I always end any of my talks with this, you need to collaborate with experimentalists, always. Otherwise, you're just developing models and doing stuff which maybe no one would care about. Thank you. Sorry, before the thank you. The most important part. So these are the people who did the work. Omer Kaspi did most of the machine learning work. Olga did all the pixie measurement. Hadar did the work on the photovoltaic, and Avi also initiated, did the work on the metal oxide. And these are our collaborators. These are the funding. Thank you very much.
We have time for a few questions. So well, I have one quick. So in your opinion, what about like the terminology itself of chemoinformatics and cheminformatics? You know that we know that there is a lot of ambiguity.
Ask them. they're expert in this terminology.
It's not an issue to discuss.
Okay. All right. Okay. So let's move to another one.
I use the term chemoinformatics, but just because I like the O.
No, in terms of terminology, I would say I can. You associate chemoinformatics, whatever, with its application to biology, so targets, ligands, etc. But it is not true. It's very a little bit confusing to me, because to me, what is a difference between material informatics and chemoinformatics? And this is the question when you use as descriptors some parameters issued from experiments, not from molecular graphs, molecular structure itself. This is actually, it makes a difference, otherwise you use exactly the same, with dyes or whatever.
Yes, but yes and no, because you can also take materials and use with them. So basically, you're saying if I'm looking at the materials, okay, suppose I was able to calculate a molecular descriptor for the material, for the solar cells. This would be classical chemoinformatics in your view?
Yes, well, let's say if descriptors are calculated directly from molecular graph, this is to me, so we had projects with viscosity or ionic liquids, whatever, and there is no difference at all compared to when we modeled biological activities. So the same descriptors, the same machine learning methods, the same validation scheme, etc. Nothing different.
I can agree to this. The line between material informatics and what I called here classical chemoinformatics to focus more on drug discovery is maybe a little blurred, but I see that Alex is nodding.
We're not allowed to discuss this. I really don't think it matters, right? There are informatics techniques, descriptors are descriptors. So if there is material science, there is material informatics. There is biology, there is bioinformatics. There's chemistry, cheminformatics. I don't think when you calculate DFT properties, right, and use those in machine learning techniques, what's that?
So we can discuss this during the coffee break.
Okay.
Thank you very much.